Right now, above your head, inside your chest, filling every inch of the room around you, there is a field with no colour, no smell, no weight you could ever press your hand against. It has no edges. It doesn't stop at the walls. It doesn't stop at the atmosphere, or the orbit of the moon, or the edge of the observable universe. It is the reason your body has mass at all. The reason atoms hold together long enough to become a hand, a heartbeat, a face looking at a screen. Physicists call it the Higgs field, and according to the best measurements we have ever taken of it, that field may currently be sitting in the wrong place. Not obviously wrong, not urgently wrong, but wrong in a very specific, very quiet, very well documented way. Wrong enough that when theoretical physicists first ran the numbers after 2012, several of them went back and rechecked their own calculations before they were willing to say the result out loud. This isn't speculation from the fringes of the internet. This is published physics, built from real data collected at CERN, the European laboratory that straddles the border of France and Switzerland. The same lab that confirmed this field's existence in the first place. The papers exist. The equations exist. The number at the centre of all of it exists, sitting in journals like Physical Review Letters and Nature Physics, footnoted and peer-reviewed, and mostly ignored by anyone who isn't a theoretical physicist. And what that number quietly implies is this. The vacuum of space, the nothing that fills 99.9% of the universe, the emptiness you assumed was the most stable, most boring, most settled thing in existence, might not be at the bottom of its own energy landscape. It might be resting on a ledge that has held for billions of years, a ledge that current physics says will, eventually, give way. If that is true, and we are going to be honest about every place where if still applies, then somewhere in the vast dark, at some unknown moment, a bubble smaller than a proton could form, one that doesn't stay small. It would expand outward at very nearly the speed of light, rewriting the laws of physics as it goes, and there would be no signal, no light, no gravitational wave, nothing at all that could ever arrive ahead of it to warn us it was coming. That's the shape of tonight's descent. Not an asteroid, not a solar flare, not anything with a countdown clock. Something stranger and colder. The possibility that the ground floor of reality itself is not where we've always assumed it to be. If that thought just shifted something in your chest, good. That's the right response, and it means you should stay for what's coming, because this gets stranger the deeper we go. Hit subscribe before we start. Drop a comment telling us where in the world you're watching this from, and if you've got a theory about what could actually trigger something like this, leave it below. We'll be circling back to that exact question later. Turn the lights down, take a slow breath, because the thing that gives your body its mass might be one push away from ending everything. And tonight, we're going all the way to the bottom of that idea. Let's start with the picture most of us grew up with, the one that feels so obvious we never bothered to question it. Empty space is empty. That's the whole point of the word. Vacuum means nothing, means zero, means the calmest possible state anything could ever be in. Textbooks describe the vacuum of space as the universe's resting position, the energetic equivalent of a ball sitting at the bottom of a bowl. It can't roll any lower. There's nowhere left to fall. Physicists even have a specific term for this lowest possible state, the ground state. And for most of the 20th century, that's exactly how we treated the vacuum. As ground, as floor, as bedrock. The one thing in an uncertain universe we could stand on and trust. Filling that vacuum, invisible and undetectable by any of our five senses, is the Higgs field. Picture the whole universe submerged in something like an ocean of syrup, except this syrup has no surface, no edges, and no possible way to drain away. Every particle that exists is constantly swimming through it. Some particles, like photons, slide through that syrup without any resistance at all. That's why light has no mass and can travel at the ultimate speed limit of the universe. Other particles, like electrons and quarks, drag through it, get slowed down, get weighed down, and that drag is what we experience, at the scale of a human body, as mass itself. Without that field, nothing would stick together. Atoms wouldn't form, stars wouldn't ignite, the word solid would have no meaning, because nothing would have enough mass to resist anything else. The Higgs field isn't decoration, it's the reason stuff is a coherent concept at all. It sits there, everywhere, all the time, quietly doing the most fundamental job in physical reality. And it does this job, according to the standard picture, from the calm, secure position of the lowest possible energy state, the bottom of the bowl, nowhere left to fall. That was the comfortable story for decades, but there's a number buried inside this story that most people have never heard. One that theoretical physicists started passing between themselves like a note nobody wants to read out loud. It's a number tied to the mass of the Higgs boson, the particle whose discovery in 2012 made front-page news around the entire planet. 125.1 billion electron volts. Hold on to that number. We'll come back to it, and when we do, it will not sound like good news anymore. To understand why that number matters, you have to go back to a moment that had nothing to do with headlines or discovery announcements. A quiet, almost bureaucratic moment in 1964, when a small handful of physicists working independently in different countries were all staring at the same uncomfortable hole in their equations. The problem they were wrestling with was embarrassingly basic. According to the mathematics of particle physics at the time, particles should have had no mass at all. None. The equations were elegant, symmetric, and beautiful, and they described a universe that could not exist because nothing in it would ever weigh anything. Real electrons have mass. Real quarks have mass. The universe we actually live in was refusing to match the universe on the chalkboard. A Belgian physicist named Robert Brout, working with his colleague Francois Englert, proposed a fix. Independently, a British physicist named Peter Higgs arrived at something almost identical. The idea was strange, even by physics standards. What if there was a field, invisible, filling all of space that particles interacted with? And what if that interaction was the actual source of mass? Not a property particles carried on their own, but something borrowed, moment to moment, from the field itself. Higgs submitted his paper to a physics journal in 1964. It was initially rejected. The reviewers weren't hostile, they simply didn't see why anyone would need a new invisible field just to patch a mathematical inconvenience. He rewrote it, resubmitted it, and it eventually appeared in print, one modest paper among thousands published that year, making a wild claim that would take nearly half a century of engineering, money, and sheer stubbornness to actually test. The problem was, nobody could see a field. You can't point a telescope at empty space that has mass-giving properties and expect a picture. What you can do, in principle, is knock the field hard enough that it ripples, hard enough to briefly shake loose a particle, a physical, detectable object that would be direct evidence the field itself was real. That particle is the Higgs boson, and producing it required smashing protons together at energies and precision that, in 1964, didn't exist anywhere on Earth. It would take until the year 2008 for construction to finish on a machine built specifically for a job like this, the Large Hadron Collider. A ring 17 miles in circumference, buried underground near Geneva, cooled colder than deep space itself so its magnets could bend beams of protons around the loop at velocities within a hair's breadth of light speed. Two beams, travelling in opposite directions, smashed into each other millions of times per second, each collision a tiny recreation of conditions that hadn't existed since a fraction of a second after the Big Bang. For years the machine ran. Data piled up. Two independent detector teams, named Atlas and CMS, sifted through mountains of collision debris, looking for one specific, extraordinarily rare signature. A bump in the data that shouldn't be there unless a Higgs boson had briefly existed and immediately decayed into other particles. On July 4th, 2012, both teams announced they'd found it. The auditorium at CERN was packed. Peter Higgs was in the audience, 83 years old, watching decades of theoretical work finally confirmed by a machine that hadn't existed for most of his career. People have described him wiping his eyes. The room applauded for what felt, by scientific conference standards, like an unusually long time. News networks around the world ran the story that evening. Physicists had found the God particle. A nickname the actual physicists hated, but one that stuck anyway, because it made for a better headline than "Scalar boson associated with electroweak symmetry breaking." It was, by any measure, a triumph. It completed the standard model of particle physics, the framework that had successfully predicted nearly every experimental result in the field for 50 years. Higgs and Englert shared the Nobel Prize in Physics the following year. Brout had passed away before he could share in it, which is its own quiet sadness sitting at the edge of this story. But here's the detail almost nobody outside particle physics noticed that night. Buried inside the celebration, inside the champagne and the group photos and the news segments, the Higgs boson had a mass. Of course it did. Every massive particle does. And that mass had a specific measured value: 125.1 billion electron volts. The number we set aside a few minutes ago. Nobody in that auditorium was thinking about what that particular number would mean once you combined it with something else. Another mass, measured separately, belonging to a completely different particle called the top quark. On its own, the Higgs mass was just a confirmation, a box checked, a prediction fulfilled. It would take a few more years, a lot more precision, and some very uncomfortable graph paper before anyone realized that number wasn't just completing an old theory. It was quietly opening a door into a much darker one. That door didn't open all at once. It opened the way most unsettling discoveries do in physics. Slowly, through years of refining a measurement that, at first glance, looked like nothing more than decimal point housekeeping. Once the Higgs boson's mass was locked in, theorists did the obvious next thing. They plugged that number into the equations describing the Higgs field itself to map out its full energy landscape. Not just the shape of the field here in our low-energy universe, but the shape it would take across every possible energy scale, all the way up toward the extreme conditions of the early universe. Think of it as taking a single confirmed point on a map and using known physics to extend the terrain outward in every direction, checking whether the ground stays solid the whole way, or whether somewhere out past the edge of what's currently mapped, it drops away into a canyon nobody had drawn in yet. To do that calculation properly, you don't just need the Higgs mass. You need the mass of the top quark, the heaviest known fundamental particle, first observed at Fermilab near Chicago back in 1995. The top quark's mass acts like a second load-bearing beam in this calculation. Get both numbers precisely enough, run the equations, and the shape of that energy landscape falls out of the math whether anyone wants it to or not. Physicists ran it, and what came out was not the shape anyone had been hoping for. The Higgs field, according to these calculations, sits at a point that is stable at the energies we experience in daily life. But as you extend the landscape outward toward far higher energies, the curve doesn't stay flat, and it doesn't rise into a wall the way a truly stable universe would need it to. Instead, using the best available central values for both masses, it slowly, gently dips, and somewhere far beyond any energy we've ever directly probed, it appears to fall to a lower point than the one we're currently sitting at. Not a cliff, a slope, almost imperceptible at first, that becomes a genuine drop the further out you go. A team of physicists, including researchers publishing in journals like Physical Review Letters through the 2010s, ran these calculations independently and kept arriving at versions of the same uncomfortable shape. That result has a name in the literature, and it isn't apocalyptic sounding at all, which somehow makes it worse. It's called metastability. Not unstable, not collapsing. Metastable. A very specific, very dry technical term that describes something sitting in a state that looks stable, feels stable, behaves in every practical sense exactly like a stable state, while mathematically resting one level above the actual lowest point available to it. Several theorists rechecked the inputs. not because they suspected fraud or error in the collider results. The Higgs and top quark masses have been measured and cross-checked repeatedly, at CERN and at Fermilab, using different detectors, different methods, different collision energies, and they keep landing in the same narrow range. They rechecked because a result like this, once it survives that many independent checks, stops being a curiosity and starts being something you have to sit with. Multiple papers through the 2010s, including work refining the calculation with ever more precise top quark data, kept landing in almost exactly the same place. Our vacuum lies extremely close to the boundary between two very different fates, and depending on exactly where the top quark mass falls within its measured uncertainty, we are either just barely stable or just barely not. That word, barely, is doing an enormous amount of work in that sentence, and it deserves to be unpacked slowly, because barely is where all of tonight's dread actually lives. Here's a way to hold this in your hands. Picture a marble resting inside a bowl that sits on a shelf. As long as the marble stays in the bowl, it can wobble, it can roll a little from side to side, and it will always settle back to the same low point, because the bowl's curve brings it home every time. That's a genuinely stable system. Nudge it and it corrects itself. Now picture that bowl sitting near the edge of the shelf, and right past the shelf's edge, the floor drops away into a stairwell that keeps going down for a very long way. The marble, sitting quietly in its little bowl, looks exactly the same as it did a moment ago. It behaves exactly the same for small nudges, but it is no longer resting at the true bottom of everything available to it. It's resting at a local bottom, a comfortable dip that happens to sit on a ledge, with a much deeper floor waiting somewhere below, out of sight, past the edge of the shelf. That's the difference between what physicists call the true vacuum and what we may currently be living inside, the false vacuum. Our universe, right now, in this exact quiet moment, may be the marble in the bowl on the shelf, stable enough to survive 14 billion years of cosmic history without incident, calm enough that stars ignite and planets form, and none of it looks remotely precarious from the inside, while still, according to the mathematics, not resting at the true, final, lowest point that the underlying physics actually allows. And that's precisely what metastability means, stripped of the jargon. Not doomed, not collapsing, but perched somewhere that could, in principle, give way. A stability with an asterisk attached. A calm that has held for a very long time, without being the same thing as permanence. The analogy has a limit, and it's worth naming honestly, because a marble on a shelf is a passive object, waiting for something, your hand, an earthquake, a gust of wind, to come along and knock it over the edge. The vacuum of space doesn't need any of that. It doesn't need a hand, it doesn't need a nudge from outside at all. And that detail, once you actually sit with it, is far stranger and far more unsettling than anything a marble could ever teach you, because it means the falling, if it ever happens, wouldn't need a cause. What then could possibly tip a balance that has held steady since before the first galaxy formed? What does a universe even look like the instant before it decides, with no warning, no external push, no dramatic countdown, to fall the rest of the way down? The mechanism has a name that sounds almost too small for what it describes: quantum tunneling. At the scale of individual particles, the universe does not obey the tidy rules your everyday intuition was built on. A particle sitting behind a wall of energy it doesn't have enough strength to climb over can, on rare occasions, simply appear on the other side. Not by breaking through, not by finding a crack. It essentially borrows its way across, for a heartbeat, using nothing but the strange permissiveness of quantum probability. This isn't speculative exotica. Tunneling is why the sun burns at all, since without it, the protons fusing in its core wouldn't have enough energy to overcome their mutual repulsion, and every star in the sky would go dark. It's also the working principle behind real, functioning electron microscopes sitting in laboratories today. Tunneling is not a theory on trial. It is measured, engineered, and used. Apply that same principle to the Higgs field, resting where it currently sits, and the picture stops being about a single particle sneaking through a wall, and becomes something with almost unbearable stakes. Somewhere, in some impossibly small pocket of space, smaller than a proton, smaller than anything you could ever picture as an object, the field doesn't need to be pushed. It can simply tunnel. It can spontaneously drop from that resting point into the deeper, truer floor beneath it, for no reason, with no warning, without a single particle colliding into another, without a single cause a physicist could point to and say, that's what did it. The event would be, in the most literal sense of the word, uncaused. A roll of quantum dice that space has apparently been making, silently, everywhere, for the entire history of the universe, and simply hasn't yet lost. Once that tiny pocket exists, physicists call it a bubble of true vacuum, it doesn't stay small. It becomes the seed of everything that follows, and everything that follows happens fast enough that the word warning stops meaning anything. Picture a frozen lake in the last days of winter. Ice that looks solid across its entire surface, cold enough and thick enough to walk on. Somewhere beneath that ice, in one specific spot too small to see, the structure gives way first. Not because anyone stepped there, not because the sun hit that patch harder than any other, but simply because that was the weakest point the moment happened to find. Once that first crack opens, it doesn't stay contained to that one spot. It races outward through the rest of the ice, and the whole lake's fate was decided in that first, invisible failure. A bubble of true vacuum works the same way, except there is no ice around it to slow it down, and no shore to stop the crack from reaching. It expands, and it expands at very nearly the speed of light, the true, absolute limit at which anything in this universe is permitted to travel. That single detail is the reason this scenario carries a particular kind of dread that almost nothing else in physics does. Every disaster our species has ever prepared for gives us something ahead of it. A shockwave outruns the blast that made it. Light from a dying star reaches us years before its true collapse finishes playing out, giving astronomers something to study before the object is gone. Even light from an exploding star arrives before its damage does, if the damage ever reaches us at all. Every warning system humanity has ever built, sirens, satellites, seismographs, telescopes, depends on one basic assumption: that something can travel ahead of the danger and tell us it's coming. A bubble of true vacuum breaks that assumption completely, because nothing can outrun it. Nothing is faster than light, and this bubble's wall moves at very nearly light speed itself, which means there is no possible signal, no flash, no gravitational wave, no burst of radiation that could ever get ahead of it and reach us first. Whatever hits you at the same instant you would have first learned it existed. There is no cosmic siren for this. There is no telescope aimed correctly enough to catch it early, because early isn't a category this event allows. And inside that expanding wall, physics itself doesn't just get destroyed, it gets rewritten. Cross into the bubble, and you are no longer in a universe where the Higgs field rests on the ledge we've been living on. You're in the universe where it settled at the true, lowest floor beneath us. The deep basement metastability had been quietly hiding the whole time. In that deeper state, the masses of fundamental particles are different. The strength of the forces holding atoms together is different. Chemistry, as a working concept, does not survive the transition. Neither, for that matter, would you, or the atoms making up the ground beneath your feet, or the ground itself. This isn't damage the way an earthquake or a fire is damage. It's a substitution, one entire physical rulebook swapped out for another, moving outward from a single point at the one speed nothing in existence is fast enough to escape. Given all of that, the only honest question left is simple. How worried, precisely, should you be about this happening anytime soon? And here, remarkably, physics offers something that sounds, at first, like real comfort. Multiple groups of theorists, using the measured Higgs and top quark masses, run through the equations describing how quickly a bubble like this should form at any given moment, anywhere in space, have calculated the average waiting time before a decay event like this should be expected to occur somewhere in the observable universe. The numbers that come out of those papers are almost impossible to hold in your head, honestly, because the units aren't years, or even millions of years. They're numbers that dwarf the current age of the universe itself so completely that the current age of the universe barely registers as a fraction of them. Estimates stretching out to figures on the order of 10 to the hundreds of years, numbers with more zeros trailing behind them than there are stars in every galaxy combined. Compared against a lifespan like that, the entire 14 billion year history of the cosmos so far, every star that has ever burned, every galaxy that has ever formed, is not even a rounding error. It's closer to the time it takes to blink, measured against the lifespan of a redwood tree, that hasn't even finished germinating yet. That is the number physicists reach for when they want to reassure a nervous public. And reasonably so. On its face, it says the odds of this happening in your lifetime, or your species' lifetime, or the lifetime of the sun itself, are so vanishingly small they might as well be zero. But sit with that number for more than a few seconds, and a second, quieter fact starts to surface underneath it. One that doesn't get repeated nearly as often, because it's far less comfortable to say out loud. That entire survival estimate rests on knowing the top quark's mass and the Higgs boson's mass with extraordinary precision. And we don't. Not quite. Our measurements have narrowed steadily since 2012, but there is still a small margin of uncertainty attached to both numbers, and the survival time calculation is brutally sensitive to exactly where, inside that narrow margin, the true values actually sit. Nudge the top quark's mass by an amount smaller than the width of the uncertainty bars physicists already work with, and the picture doesn't shift gently. It can swing the entire vacuum from a state that's essentially stable for the rest of cosmic time, to one that's metastable with a specific, calculable half-life, to, depending on which side of the range you land on, a vacuum that current models can't even confidently rule out as being unstable already. Actively rolling, right now, everywhere, all at once. Too slowly for us to have any way of noticing yet. That is not a small caveat sitting quietly in a footnote. That is the entire conclusion of the analysis, hinging on a decimal point we have not yet nailed down. And it means every time you hear a physicist say, with real confidence, that vacuum decay is nothing to lose sleep over, what they are actually reporting is our best current estimate, built from our best current measurements, sitting on a foundation that has moved before and could move again as our instruments get sharper. The reassurance is real. It is also provisional in a way most reassurances in physics quietly aren't. And even if we take the most optimistic reading of those numbers at complete face value, even if our particular patch of universe really is sitting on a survival estimate longer than almost anything else in existence, that number was only ever calculated for decay happening here, starting from us, starting now. It says nothing at all about somewhere else. It says nothing about somewhen else. Because if this process really is uncaused, really is governed by nothing but quantum probability rolling its dice across the entire volume of space, then there is no reason at all to assume the very first bubble ever to form did so recently, or nearby, or on any timeline connected to human history at all. The observable universe is old, roughly 13.8 billion years old, and vast beyond anything the word vast was originally built to describe. If a bubble of true vacuum nucleated somewhere far across that volume, billions of years ago, in some galaxy we've never even resolved through a telescope, its wall has been expanding at very nearly light speed for all of that time since. Which means it could, this very moment, already be crossing the space between that origin point and us. And because nothing can outrun it, and no light or gravitational signal could ever race ahead of its own leading edge, we would have exactly zero advance notice. It wouldn't announce itself in tomorrow's sky. It wouldn't show up as some faint dimming. It would simply reach us the instant it reaches us, converting everything it touches at the one speed limit nothing else in this universe is fast enough to escape. There is no comfortable way to fully close that particular door, because it isn't a door our physics currently has a key for. But there is one piece of real, tested evidence that at least tells us something honest. Not a guarantee, but a genuine data point, earned the hard way over decades of actual experiments rather than pure theory. Since the Large Hadron Collider first switched on, it has produced hundreds of trillions of proton collisions, each one briefly recreating energy densities that haven't existed naturally since fractions of a second after the Big Bang. Every one of those collisions was, in a very real sense, a tiny, controlled poke at the vacuum itself, an attempt to see whether concentrating that much energy into that smaller point might be enough to nudge the field over its ledge. It never has. Not once. Not in over a decade of continuous operation and multiple energy upgrades. And the Large Hadron Collider isn't even close to the most violent thing regularly striking our little corner of the universe. Cosmic rays, particles accelerated by distant supernovae and other extreme astrophysical events, slam into Earth's upper atmosphere constantly, and some of the highest energy cosmic rays ever detected carry energies far beyond anything humanity's most powerful collider has ever produced, dwarfing it many times over. Those collisions have been happening in the atmosphere above your head for the entire history of the planet, roughly 4.5 billion years of it. At energies our own machines can't even approach, and the vacuum has, so far, held every single time. That's genuinely, carefully reassuring, and worth taking seriously as reassurance, not just as a talking point, but it comes with an honest limit that no physicist worth listening to will hide from you. All of those collisions, from the Large Hadron Collider and from cosmic rays alike, are still just probing one specific, narrow slice of the energy landscape. The slice reachable by particle collisions here, in our regime, under our familiar 4 fundamental forces behaving the way they always have. They tell us almost nothing certain about what happens at energies unimaginably higher still, up near what's called the Planck scale, the energy level at which gravity itself is expected to stop being the gentle background force we experience and start mattering just as much as the other 3 fundamental forces in determining how the vacuum actually behaves. And that is the honest, unglamorous edge of what we currently know. Every calculation about the Higgs field's true fate, every survival estimate, every reassuring comparison to the age of the universe has been built almost entirely without gravity in the picture, because we don't yet have a working theory that unifies gravity with quantum mechanics at those extreme energies. Some physicists, working with certain versions of that missing unification, have published calculations suggesting gravity's influence would actually make our vacuum more stable than the simplest picture implies, effectively deepening the shelf, making the true floor beneath us harder to reach. Other physicists, running different assumptions through equally legitimate frameworks, get the opposite answer. Gravity makes the fall easier, not harder, and the true vacuum sits closer than the simple calculation ever suggested. Both conclusions exist in the published literature. Both were reached honestly. And right now, with the tools currently available to physics, nobody can tell you with confidence which one is actually true. That gap, that specific, named, acknowledged gap in human knowledge, is where this story stops being a settled question and starts being something else entirely. A live, contested edge of physics, sitting exactly at the point where our best equipment runs out of reach and our best theories start disagreeing with each other about what waits on the other side. That gap between competing gravity models isn't just an academic disagreement sitting in some unread appendix. It's the difference between a universe that's almost certainly fine and one that isn't. And nobody currently knows which side of that gap we're standing on. So let's be precise about what not knowing would actually feel like if the worse answer turned out to be the true one. It would not feel like anything. There would be no tremor, no darkening sky, no instrument spiking red in some observatory basement moments before the end. A supernova gives its galaxy months of warning light. An asteroid gives astronomers years, sometimes decades, to calculate a path and consider options. Even the worst earthquake gives you a few seconds of tremor before the ceiling comes down. Vacuum decay gives you nothing, because the wall of the bubble moves at the same speed as any signal that could ever tell you it's there. The information and the event arrive together. There's no gap between warning and outcome for your nervous system to occupy, because your nervous system, along with every atom that composes it, would already be inside the new vacuum before a single nerve had time to fire. That's worth sitting with honestly, because it's not the same shape of fear most people carry about the end of the world. There's no suffering built into this scenario. No pain, no fear, no final moment of understanding what's happening. Because understanding takes time, and time is precisely what this event does not leave you. It isn't a catastrophe in the way fire or flood or war are catastrophes. It's closer to a light switch for existence itself, on, then, without any perceivable seam, simply reconfigured into something that isn't you, isn't Earth, isn't anything resembling the universe you were standing in a moment before. If it happens, nobody mourns it, because mourning requires survivors, and this leaves none, anywhere, ever. Which raises an uncomfortable but fair question. If we can't feel it coming, and we can't feel it happen, how confident can physicists actually be about how close we are to it? The honest answer starts with the measurements themselves, and just how thin the margins really are. The Higgs boson's mass, as measured by the ATLAS and CMS detectors at CERN, has been pinned down to within about 0.1% of its central value. Remarkably precise by any standard in experimental physics. The top quark's mass is measured a little less tightly, with an uncertainty of roughly 0.5%, thanks largely to how the top quark decays almost instantly into a spray of other particles, making it much harder to pin down cleanly than the more stable particles physicists are used to measuring. 0.5% sounds small. It sounds, frankly, like the kind of number you'd forgive in almost any other context. A rounding error nobody would think twice about. But the vacuum stability calculation doesn't treat that 0.5% gently. Run the top quark mass at the low end of its currently accepted range, and the equations describing the Higgs field's energy landscape come out looking essentially stable. A bowl with real walls, extending upward comfortably, with no lower floor waiting anywhere accessible. Run it at the high end of that same accepted range, and the landscape tips toward instability outright. No metastable ledge required, just a slope leading down that current calculations suggest could, in principle, already be underway. Our best measured value happens to sit almost exactly between those two extremes, which is precisely why the honest technical term physicists reach for isn't stable or doomed, but consistent with either, depending on where inside our own uncertainty the true number actually lives. That's not a comfortable sentence, but it is a true one, and it deserves to be repeated slowly. The difference between a universe with a functionally infinite future and a universe already quietly rolling toward its own end may come down to a measurement precision we haven't achieved yet, sitting inside decimal places smaller than the width of the uncertainty bars on a graph most people will never see. Future colliders. Proposals under discussion, some decades from construction, if they're ever built at all, might sharpen that number enough to finally settle which side of the line we're actually standing on. Until then, the honest position isn't fear, and it isn't comfort. It's living inside an open question that happens to be existential. It helps at this point to place vacuum decay next to the other ways this could all end, because the comparison sharpens exactly what makes it different, and exactly why it earns a category of its own. An asteroid capable of ending civilization would need to be tracked, aimed, and unlucky, and we now catalogue the overwhelming majority of large near-Earth objects well enough to rule most of them out for centuries. A supervolcano needs magma, pressure, geology building toward a specific point beneath specific ground, and it leaves geological fingerprints scientists actively monitor. Nuclear war needs decisions, human beings, choosing, launching, retaliating. A chain of choices that, however terrifying, at least involves agency somewhere in the sequence. Every one of those scenarios requires something: a rock on the right trajectory, a fault line under the right strain, a finger on the right button. Vacuum decay requires none of that. It doesn't need a rock, a fault, or a finger. It doesn't need malice, error, or even matter. It needs nothing except the field's own probability catching up with itself, somewhere in the ordinary passage of time. No external trigger, no villain, no accident report to be written afterward, because there'd be no one left to write it. In a strange way, that makes it the most impersonal catastrophe available to physics. Not something that happens to the universe, but something the universe might simply do to itself as a basic consequence of the numbers it was built from at the very beginning. Zoom out far enough, and cosmology offers an idea that makes this even stranger. A hypothesis called eternal inflation, taken seriously by a meaningful portion of theoretical cosmologists, though still very much unproven. It suggests our Big Bang wasn't a singular event, but one bubble of settled, ordinary spacetime nucleating out of a much larger, still inflating substrate, and that this process may never fully stop, spawning countless other bubble universes, endlessly, in a volume of reality so much larger than our own observable patch, that universe, in the everyday sense, might be the wrong word entirely for what we actually live inside. If that picture is right, then bubbles of collapsing false vacuum wouldn't be a hypothetical local event confined to worrying about our own galaxy. They'd be a standing feature of the wider structure reality is built from, happening elsewhere, constantly, as part of the ordinary background hum of a much larger cosmic process, most of it entirely unreachable, unobservable, and irrelevant to us. Except for the one detail that decides everything: whether that process has already reached, or will ever reach, this particular bubble. Against a backdrop like that, one more number deserves to be said plainly, because it puts the entire conversation into a kind of scale most people never think to apply to their own field of study. Humanity has been capable of even asking this specific question, measuring the Higgs boson's mass, calculating the shape of its field's energy landscape, running the equations that produce a survival estimate at all for roughly 70 years, and really, precisely, only since 2012. 70 years, set against a question that only matters across a timescale of billions upon billions of years. That ratio is difficult to even express honestly without it sounding exaggerated, but it isn't. It is something on the order of 1 part in 100 million. A sliver of time so thin against the span the question actually concerns that our entire scientific relationship with this problem could be erased, and it would barely register as a rounding error in the ledger of cosmic history. We are, by any fair reading of that number, almost impossibly recent to this conversation. Every generation before ours lived out full lives never once knowing this question existed to be asked, and every one of them was, by definition, exactly as safe or exactly as doomed as we are right now. The vacuum's actual state doesn't care whether anyone is measuring it. What changed in 2012 wasn't the universe's stability. What changed was that, for the first time in the roughly 300,000 years modern humans have existed, and the 14 billion years the universe has existed before us, one particular species, on one particular rock, finally built an instrument sharp enough to ask the ledge a direct question, and got an answer too close to the edge to fully relax about. There's something almost dizzying in sitting with that fact directly. We are not privileged observers watching this question from a position of safety and comfort, granted extra time to figure it out before it matters. We are latecomers, arriving at the exact moment our tools became sharp enough to notice the shape of the problem, after 14 billion years during which the universe had already, apparently, been sitting on this same ledge the entire time, indifferent to whether anyone would ever be around to measure it. And yet, turn that same fact very slightly, look at it from a different angle, and it stops being only frightening. It becomes something closer to remarkable, maybe even something worth calling sacred, in the plainest, least mystical sense of that word. Out of everything the vacuum could have done across 14 billion years, everything it could have collapsed into at any random moment, governed by nothing but quantum probability, it didn't. Stars formed anyway, galaxies assembled anyway. On at least one unremarkable planet orbiting an unremarkable star, chemistry organized itself into something that could eventually turn around, measure the field it was made of, and understand, correctly, rigorously, honestly, that its own existence had never been guaranteed by anything more solid than a ledge that happened to hold. That is not a small thing to be true about a species. Every conscious moment you have ever had, every sunrise, every ordinary Tuesday, every argument and meal and quiet, unremarkable afternoon occurred inside a universe that, according to its own physics, was never obligated to keep existing for any of it. The horror in that fact, and the wonder in that fact, are not two separate feelings sitting side by side. They are the exact same fact, examined from two directions, and the only real difference between dread and awe here is which direction you happen to be facing when you let it land. So return, for a moment, to where we started, to the quiet claim that the field filling every inch of space, the one responsible for your own mass, for the solidity of the ground and the weight of your own body, might not be resting exactly where we always assumed it was. That claim hasn't gotten any less true across everything we've walked through tonight. If anything, it's gotten heavier, because now you understand precisely how it would happen, why no signal could ever precede it, and how thin the numbers are that currently stand between almost certainly fine and we don't actually know. Nothing about that has to happen tomorrow. Nothing about it has to happen in the next trillion years either, if the more optimistic calculations are the correct ones. But the honest current state of physics will not let you say it can never happen at all. And that single unresolved word, never, is the entire shape of what we've spent this time inside. So here's the question worth carrying with you after this ends, the one with no comfortable answer waiting on the other side of it. If the ground beneath all of existence has always been this uncertain, and every single day you've ever lived was, without your knowledge, borrowed time standing on a ledge, does that make the life you're living less meaningful? Or is it the only thing that ever actually made it matter at all? If this changed how solid the ground feels beneath you tonight, that's the point. Hit like, subscribe, and tell us in the comments what you'd want to know first, if we ever did find a way to measure which side of that ledge we're really standing on.